All right, strap in, everyone. Let's dive headfirst into the quantum realm. Today's deep dive is all about Grover's algorithm.
Ah, yes. A fascinating one.
We're going to be breaking down Jörg-Owe Schneppat's paper.
Okay.
Groveralgorithm.pdf. Pretty straightforward title.
Right to the point.
Now, I know quantum computing can sound a bit like something out of Star Trek.
A little bit, yeah.
But this stuff has some serious real-world potential, especially for those of you interested in things like data science and cryptography.
It really does. And Schneppat, he does a good job, I think, of laying out why.
Yeah, so let's break this down.
Okay.
What exactly is Grover's algorithm? What problem is it trying to solve?
So at its core, Grover's algorithm is all about searching.
Searching, okay.
Like finding a specific piece of information in a massive jumble of data. Schneppat actually uses a really good analogy in his paper. Let me see if I can find it.
Yeah, because I was thinking like finding a needle in a haystack.
It's like that, yeah. But he uses, oh, here it is. He talks about searching for a specific book in a vast library.
Okay.
I like that. With millions of books. And, you know, in the classical world, how would you do that? You'd have to go shelf by shelf, book by book. It could take forever.
Yeah. Especially if you don't have a good library catalog system.
Right. But Grover's algorithm leverages the strangeness of quantum mechanics to speed up that search dramatically, like exponentially faster.
Well, hold on. Quantum mechanics? How does that even play into searching for something?
Well, it all comes down to this concept called superposition. In the quantum world, a particle can exist in multiple states at the same time. It's kind of mind-bending, I know.
Yeah, a little bit.
But imagine, instead of checking each book one by one, you could somehow check all the books in the library simultaneously.
That's pretty wild.
That's essentially what Grover's algorithm allows you to do. Schneppat breaks it down really well, how it exploits this superposition principle.
Okay, so I'm following so far. We're using this quantum superposition to check tons of possibilities at once.
Right.
But how does it actually pinpoint the right answer? The right book in our library analogy?
It's pretty ingenious, actually. It uses this two-pronged approach. First, there's something called amplitude amplification.
Amplitude amplification. That sounds...
It sounds complicated, but it's like, imagine you have all these different sounds playing at once, and you want to isolate just one of those sounds, make it louder than all the others. That's kind of what amplitude amplification does.
So it's boosting the signal of the right answer, making it stand out from the noise.
Exactly. And the way it does that is by, well, think of it like turning up the volume on the correct answer while simultaneously turning down the volume on all the incorrect ones.
Okay, that makes sense.
Yeah, and Schneppat has some really good visuals in his paper to illustrate this. It's easier to see than to describe.
So we've got this amplitude amplification, making the right answer louder, so to speak. But how does the algorithm even know which answer to amplify in the first place?
That's where the second piece comes in, something called the oracle function.
The oracle function. Okay, that sounds mysterious.
It is, kind of. Schneppat describes it as a black box that can identify the target item.
Without actually knowing anything about the problem itself. Like it just magically knows.
In essence, yes. It's a bit of a simplification, but for our purposes, you can think of it that way. It's this function that can say yes or no to the question, is this the item we're looking for? But it doesn't know anything about the item itself.
Huh. Okay, I'm going to need a minute to wrap my head around that one. It's like having a bloodhound that can sniff out a specific person without ever having smelled them before.
That's a good analogy. It just knows.
It's a little spooky, but cool.
It is, right? So we've got these two key pieces. Amplitude amplification to boost the right answer, and the oracle function to identify it in the first place.
Right. So how does this all work in practice? How do these pieces fit together?
So the first step is to put all the possible solutions, all those books in our library, into a state of superposition.
All at once.
Yep.
Every single book is a potential candidate at this point. Then the oracle function steps in and flags the correct book. Think of it like putting a little marker on the one we're looking for.
Okay, so we've marked our target. What happens next?
Next comes the Grover operator, which is where the magic really happens. This operator basically takes that marked book and amplifies its amplitude, making it more likely to be the outcome when we finally measure the system. At the same time, it's decreasing the amplitudes of all the other books. Schneppat goes into the math in detail, but the gist is that it's focusing the spotlight more and more on our target.
Okay, I think I'm starting to see it. It's like with each step, the right answer is getting brighter and brighter, and all the wrong answers are fading into the background.
You got it.
Yeah.
And finally, we perform a measurement, which forces the system to collapse out of its superposition. And what we're left with, ideally, is the book with the highest amplitude, the one we've been searching for all along. Wow, that's amazing. We started with a jumbled mess of possibilities.
Oh, yeah.
And through this clever manipulation of amplitudes and whatnot, we've isolated the one answer we wanted. Pretty slick. Now I'm dying to know how this actually translates into real-world applications. What can we actually do with this?
Oh, well, Schnepphat, he outlines a whole range of possibilities. I mean, this is just the tip of the iceberg.
Okay, well, let's dive into those in the next part then.
Sounds good.
All right, so we've laid the groundwork for how Grover's algorithm works, but I'm really curious about where this fits in the real world. What can we actually do with this thing?
Oh, man, the possibilities, they're pretty mind-blowing. Schnepphat, he really lays out a whole spectrum of potential applications in his paper.
Okay, so what are some of the big ones? What's got Schnepphat excited?
Well, one area where Grover's algorithm could have a massive impact is cryptography.
Cryptography, so like codes and ciphers and all that.
Exactly. Imagine being able to crack complex encryption codes, like way faster than we can today. Schnepphat really dives into this, the implications for cybersecurity.
That's both exciting and kind of terrifying, right? I mean, we're talking about the codes that protect our online banking, our private messages, all of that.
Right. And Schnepphat, he's not shying away from those implications. He even suggests that Grover's algorithm, it could render some of our current encryption methods obsolete.
So we're going to need even stronger codes to keep up with these quantum computers.
Well, that's the cat and mouse game, isn't it? As quantum computers become more powerful, so too will our methods of protection need to evolve.
Yeah, it's a constant arms race.
And Schnepphat, he really highlights that tension.
Okay, so cryptography, that's a big one. What else is Schnepphat talking about?
Another area he's particularly excited about is optimization problems.
Optimization problems. Now, remind me what those are again.
Think of scenarios where you need to find the absolute best solution among a ton of possibilities. Things like optimizing delivery routes for, say, a logistics company.
Okay. Yeah.
Or maybe like financial portfolios, or even designing new materials with specific properties.
So it's like instead of just finding a needle in a haystack, it's finding the sharpest, shiniest needle in the whole stack.
Exactly. Schnepphat's research suggests that Grover's algorithm, it could be a game changer for these kinds of problems. It could help us find those optimal solutions way, way faster.
Okay, that makes sense. And of course, there's the more obvious application, just straight up searching databases.
Right. I mean, imagine being able to instantly find any piece of information in a massive unstructured database. No more waiting for search results to load, no more sifting through irrelevant information.
So like Google, but on steroids, for any kind of data you can imagine.
That's a good way to put it. Schnepphat paints a pretty compelling picture of a future where searching for information is, well, effortless.
That sounds pretty amazing. But before we get too carried away with all the awesome possibilities, let's talk about the elephant in the room, the quantum computers themselves.
Right. It's all well and good to talk about these algorithms, but we can't forget that actually building and running these quantum computers, it's a whole other challenge.
I mean, I know these things are still in their early stages, right?
They are, yeah. And Schnepphat, he acknowledges that in his paper. He talks about the limitations, the hurdles we still need to overcome.
So what are the main roadblocks? Is it just about building these things in the first place?
That's a big part of it. Building stable and reliable quantum computers with enough qubits, which are like the quantum version of bits, it's incredibly difficult.
And expensive, I imagine.
Oh, yeah. It's a huge undertaking. But there are also technical challenges, too, like keeping these quantum states stable long enough to actually run these algorithms. It's a delicate dance.
What do you mean by that? Like, what makes them so unstable?
Well, one major issue is decoherence. It's basically when the quantum states get disrupted by noise from the environment, and that leads to errors. It's like trying to build a sandcastle on a windy beach. It's really hard to keep it from falling apart.
So it's a battle against the elements, in a way.
Yeah, exactly. Schnepphat, he spends a good chunk of his paper discussing this challenge of decoherence. It's one of the biggest hurdles in the field right now.
So it's a constant balancing act. We're trying to harness this incredible power of quantum computing, but at the same time, we're fighting to keep these quantum states from just, like, dissolving.
Yeah, it's a tricky situation. And on top of all that, there's the whole issue of, cost and resource constraints. Building and maintaining these sophisticated quantum systems, it's not cheap.
So even though Grover's algorithm holds all this promise, we're still a ways off from actually seeing it in action on a large scale.
That's the reality of it, yeah. But hey, that doesn't mean progress isn't being made. Schneppat, he's actually quite optimistic about the future. He points to a lot of exciting advancements that are happening in the field.
Well, that's good to hear. What are some of the things researchers are working on to push the boundaries of Grover's algorithm?
Yeah.
What's the cutting edge look like?
Well, one area of focus is developing variations of the algorithm, tweaks and adjustments to address specific challenges. For example, Schneppat talks about how researchers are exploring ways to handle situations where there are multiple correct answers to a search problem.
Oh, right. Because the classic Grover's algorithm, it's all about finding that one needle in the haystack.
Exactly, but what if there are multiple needles? Or what if we're not even sure what we're looking for, just that it has certain characteristics?
Yeah, like we know the needle is silver, but we don't know its exact shape.
That's a great analogy. And researchers are working on adapting Grover's algorithm for those kinds of scenarios. Schneppat also discusses another interesting variation called partial search.
Partial search, what's that all about?
It's a technique where the database is divided into smaller blocks, which can be really helpful when you're dealing with incredibly massive data sets. Instead of searching the entire haystack all at once, you're breaking it down into smaller, more manageable chunks.
So it's like having a team of searchers each focusing on a specific section of the haystack, right?
Exactly. It's a divide and conquer strategy, and it can make the algorithm much more efficient.
So it seems like even though we're still early on, the world of Grover's algorithm is already pretty dynamic and full of possibilities. Mm-hmm. What does Schneppat see as the future of this field? Where are we headed?
Schneppat, he's very optimistic. He believes that as quantum technology matures, Grover's algorithm and its many variations, they're going to revolutionize a whole range of fields. Everything from, cryptography and drug discovery to machine learning and even artificial intelligence.
Wow, that's a pretty broad spectrum. What are some specific examples he gives? Like, how would this actually play out in those fields?
Well, for example, he talks about how Grover's algorithm could be used to develop new drugs and materials by rapidly searching through massive databases of molecules.
Okay, yeah. I can see how that would speed things up considerably.
Right. And he also talks about its potential in machine learning. Speeding up the process of searching for patterns in data.
So it's like giving these machine learning algorithms a turbo boost.
Exactly. And Schneppat believes that in the long run, these kinds of advancements, they're going to have a profound impact on society.
Well, I'm convinced. Grover's algorithm is definitely something to keep an eye on. It's both fascinating and a little bit intimidating to think about all the possibilities. I'm ready to hear what else Schneppat has to say in the final part of our deep dive.
Yeah.
What's on the agenda for next time?
Next time, we're going to get even more into the nitty-gritty. We'll talk about complexity analysis, really quantifying that speedup we've been discussing. And we'll also dive into some more of those fascinating variations that researchers have come up with. It's going to be a fun ride.
Sounds good. I'm ready. All right, welcome back to the show. We're wrapping up our deep dive into Grover's algorithm. We've already covered a lot of ground, but we promised to get into some of the more technical details. So let's dive in.
Yeah, I think Schneppat would approve. He really emphasizes the importance of understanding the nuts and bolts of this algorithm.
So let's start with complexity analysis.
Yeah.
You've mentioned this quadratic speedup before. Can you break that down for us? What does that actually mean in terms of, how much faster this thing is?
Okay, so imagine you have a database with, let's say, 1 million entries.
Okay, 1 million. Got it.
In a classical search, you'd have to look through, on average, 500,000 entries to find what you're looking for.
Right. Makes sense. You got to check them one by one.
Now, Grover's algorithm, because it's using this quantum superposition magic, it can do the same search in roughly 1,000 steps. It's the square root of 1 million.
1,000 versus 500,000. That's a pretty big difference.
It's huge. And Schneppat, he really drives this point home. This quadratic speedup, it becomes especially important when you're dealing with, really massive data sets.
Right, like the kind we see in, big data analytics and all that.
Exactly. It's not just a theoretical curiosity. This speedup has real-world implications. Schneppat even argues it could change the game for things like drug discovery, materials science, all sorts of fields.
Now, you also mentioned that Grover's algorithm might perform differently in different scenarios. Can you give us some examples of that? Are there cases where it's not as effective?
Well, one thing Schneppat points out is that the classic Grover's algorithm, it works best when you're searching for a single unique item. But what if there are multiple correct answers?
Yeah, that makes sense. The whole needle in the haystack thing gets a little more complicated if there's more than one needle.
Right. But thankfully, researchers have figured out ways to modify Grover's algorithm to handle those cases, too. Schneppet actually describes some of these variations in his paper. It's pretty fascinating stuff.
So it's an adaptable algorithm. We can tweak it to suit our needs.
To a certain extent, yeah. And another interesting scenario Schneppet discusses is what's called partial search. This is where you're not searching the entire database, but just the specific subset of it. It's like, you know how libraries have those little Dewey Decimal System stickers on the spines of the books?
Yeah. To organize them by category.
Right. So imagine you're only interested in books on a specific topic. With partial search, you can use Grover's algorithm to just search that section of the library, that particular category.
Okay, that's clever. It's like using a filter to narrow down your search results.
Exactly. And Schneppet points out that this can be super useful when you're dealing with really gigantic data sets. It can significantly speed up the search.
So even with all these variations and adaptations, are there any fundamental limitations to Grover's algorithm? Are there problems where it just wouldn't be the right tool?
Well, that's a really good question. And Schneppet, he's honest about the fact that Grover's algorithm, it's not a silver bullet. It doesn't offer a speed up for every type of computation.
Okay, so what are its limits? Where does it fall short?
Well, one thing to keep in mind is that it's really good at unstructured search problems, where you're essentially looking for a needle in a haystack. But for problems with a lot of inherent structure or where you already have some knowledge about the solution, it might not be as effective. It's like if you're looking for your keys and you left them on the kitchen counter, you don't need to search your whole house. You can just go straight to the counter.
Right. No need to deploy the quantum search algorithm for that.
Exactly. And even with its speedup, Schneppet acknowledges that there are certain problems where classical algorithms might still be more efficient, especially as those classical approaches continue to evolve.
So it's not always a clear-cut win for quantum computing. It's an ongoing competition.
It is, yeah. And the best approach often depends on the specific problem you're trying to solve and, the resources you have available.
Well, this has been a fascinating deep dive. We've learned so much about Grover's algorithm, from the basic principles to the potential applications and even the limitations. What are your final thoughts on this algorithm? Where do you think it's headed? What kind of impact do you think it will have?
I think Schneppet sums it up really well. He says, and I'm paraphrasing here, that Grover's algorithm, even in its current form, is a testament to the power of quantum computing. It shows us what's possible when we start to harness the strangeness of the quantum world.
Yeah, it's mind-blowing to think about. And even if it doesn't solve every problem, it's clear that this algorithm and others like it, they're going to have a profound impact on, well, pretty much every aspect of our lives.
I think so too. And what's exciting is that we're really just at the beginning of this quantum revolution. There's so much more to discover and explore.
It's an exciting time to be alive, that's for sure. Well, thanks for joining us on this journey. We hope you've enjoyed learning about Grover's algorithm as much as we have. And until next time, keep those minds curious and those questions coming.